Welcome to wrap-up lecture for chapter 19. I am going to work the last three problems from the lecture, 14, 15, and 16. We went through 15 and 16 rather quickly, and then I'm going to work one from the ACS in the energetics section. The one that I've picked to work is actually something from 131. I think that most of the questions from the material you've learned for thermodynamics in this semester is actually pretty easy as represented by the questions there, mostly about entropy increasing or decreasing and signs for delta H and delta S and how that affects delta G. So that table that I told you was important, you definitely need to know that. So make sure you look those over. But let's go ahead and get started with number 14, which we did not do at all in class. So I really want to get rid of that thing there. There we go. All right, so number 14, we are going to use data from Appendix C to estimate the temperature at which the free energy change, that's delta G, for the transformation from solid to gas is 0. So when delta G is equal to 0, we know that we have an equilibrium situation. And anytime we have a phase change, during that phase change, if we are at the phase change temperature, there exists an equilibrium between the two phases. So in this case it would be solid and gas. So we're talking about sublimation. So what we need in order to do this is, of course, we need delta H and delta S. So let's write down our equation, delta H minus T delta S. Now they're asking for the temperature. So we've talked about this in class. If I want to know what is the temperature when delta G goes from positive to negative, or in this case when it's 0, when you're at equilibrium, in both cases, you're going to set delta G equal to 0. So 0 is equal to delta H minus T delta S. Reminders, delta H is in kilojoules, S's are in joules, and temperature needs to be in Kelvin. Rearranging this equation to solve for temperature, we would bring delta H to the other side. Of course it would, I'm going to come over here with it. Of course it would be negative, and that is going to equal negative T delta S. So the negatives go away, and solving for T, I end up with delta H over delta S equals the temperature at which delta G is equal to 0. Or for other problems, when delta G, the temperature at which a reaction becomes spontaneous if delta G is in fact positive. You can use this same approach. All right. So the first thing we're going to need to do is calculate our delta H and delta S. Okay. So let me get my work in front of me here. So the equation that we're talking about is I2 solid, which is the standard state for iodine, goes to I2 gas. So when I am doing my delta H, of course it is, if this is up for sublimation, it is equal to products minus reactants. So if I look up the heat of formation of this product, it is 62.25 for iodine gas. That's the heat of formation. We're going to do products minus reactants. And then the solid, of course, is 0 because that's the standard state for iodine. Look it up in the back of your book. You'll see that it is indeed 0. So we take 62.25 products minus reactants, and we end up with our delta H of 62.25. Okay, we're going to do the same thing for S. Delta S is going to be products minus reactants as well. Now, everything that we're looking up in the back of the book is at standard state, which means 25 degrees Celsius and 1 atmosphere. So that's one of the assumptions we're going to be making, is that, and that's one of the questions in this, the second sentence up here in A, is what assumptions must you make in arriving at this estimate? Well, we are calculating delta H and delta S under standard conditions. And as we'll see in B, we're going to estimate we're going to get a temperature, and it's not going to be at standard conditions once we solve for this equation here. So that's one of the assumptions we're making, is that we're solving for delta H and delta S at standard conditions, 25 degrees Celsius, 1 atmosphere, but when we calculate the temperature for the sublimation, it is not going to be. So that is one of our assumptions. Anyway, continuing on. Products minus reactants. So we would do the same thing with S. I'm going to write it above. You look up your absolute entropies in the back. And for the solid, it is 116.73. Okay. And for the gas, it is 260.57. So as we discussed in this chapter, delta H's for elements at standard conditions is 0, but absolute entropies are not. But we calculate the change in entropy, therefore the triangle, the same way, products minus reactants. So we're going to say, that's a 0 there, 260.57 minus the 116.73. So that our entropy value for this equation is 143.84 joules per K. And my units up here for delta H were this. Okay, a couple things. One, positive delta H means it's endothermic. Of course, it's going to take some energy, input of energy. Notice it's not a lot. As I told you in class once before, if you take some iodine solid, put it at the bottom of a jar and put the lid on it, it goes right into the gas phase. Very nonpolar molecule, and therefore its forces of attraction between the molecules is, London dispersion only, and so it does go into the gas phase rather easily. Positive delta S means that we have increased entropy. Of course we have, going from a solid to a gas. So now we're going to take these two things and we're going to get that temperature for sublimation. But remember, you have to change your units. Okay, so I'm going to take my 62.25 kilojoules for delta H and put that over delta S, but I have to put that in kilojoules, so 0.1438 joules per Kelvin. So the joules cancel, kilojoules cancel out. And I end up with a Kelvin temperature, and that Kelvin temperature is 432.8 K, which is 160 C. So we are saying that the sublimation temperature at which this equilibrium occurs is 160 degrees Celsius. The assumption we made here was that when we calculated delta H and delta S, we were calculating those at standard conditions, and so we're assuming that that still holds when we put it into this equation here, that delta H and delta S aren't changing at 160 degrees. Okay, so last thing we need to do is the B part, and that is use a reference source such as Web Elements to find the experimental melting and boiling. So just mainly just looking up the melting temperature for iodine, and it's 113.7 degrees Celsius, and the boiling temperature is 184.3. Not a very high boiling temperature. And then it says to which of the values in part B is closer to the value obtained in part A. Can you explain why this is so? So 160 is certainly closer to 184. We're talking about the same phase change going to a gas. Boiling, the difference between the two is, one, this is solid to gas. Okay, so you would think that this one would be higher. Boiling is liquid to gas. And one of the reasons why, of course, they're similar, and the reason why these two are similar is because it's a similar phase change, but boiling does involve the entire container. The phase change happens throughout the container, whereas sublimation should be a more surface thing like evaporation is. So it doesn't involve the entire container going through that phase change. I guess is my way of explaining why 160 is less than 184 when you would think that this phase change would be harder to do. However, iodine does go into the gas phase rather easily. All right, so that pretty much does finishes us up for number 14. It's a good question. It combines, a lot of things from the chapter. So let's move on to number 15. I want to do number 15 again because we did it really quickly in class. I don't think you were really, your looks on your faces were rather incredulous, and I didn't show any calculation. Plus, I think I did number 15 wrong in class. I think I said something wrong on C. So I want to revisit that and then make sure that you understand why things are occurring the way that they are. So it's indicate whether delta G increases, decreases, or stays the same when the partial pressure of hydrogen is increased in each of the following reactions. So what's going on here is that we are referring to, I'm going to use this form of the delta G expression, the delta G equation. Delta G equals, so if I have a situation where I am not at equilibrium, as in this case, we are doing a Le Chatelier's principle kind of thing, and so we'd be looking at a Q. There's another value, another equation for delta G, and that is delta G naught, which is standard conditions, equals minus RT ln of K. So here we are essentially, you can use this to get delta G's from K's and back and forth and so on. This one up here is more of a Le Chatelier application, is the word I was looking for. So I'm going to use the one up top because we are changing and then we want to know what happens to delta G. So is my new delta G going to be smaller or larger than this original one? Okay. All right, so if I increase in A and C, both, hydrogen is a reactant. Okay. If I'm doing either K or Q, my expression is either K or Q. It is products over reactants. Okay. In both A and C, I am increasing the denominator of this ratio. So let's just do a little quick math. If so, we don't. All we have to do is look at this last term. So plus RT ln, and this is constants. So we're not going to do. Doesn't matter what that is. What happens to Q when the reactant, the denominator rather, in A and C decreases? So let's say we went from that ratio being 2 to that ratio being 1 because I have increased the bottom, so the denominator increased, so the ratio decreases. So if I take 2 and take the natural log of that, I get 0.693. That is the natural log of 2. If I take the natural log of 1, it's 0. So you can see that Q is decreasing. And so if this term decreases, then you'll be subtracting that from this and delta G will decrease. Okay? So in A and C, Q is decreasing, delta G decreases. In B, you're doing the opposite. You are increasing a product. And so therefore Q will increase, and if Q increases, delta G increases. All right? That's pretty much all 15 is about. Moving on to 16. All right, this one I wanted to go back to because I just gave you on faith what delta H and delta S were. And so I want to go through how those were calculated and then repeat. We did it at the end of class very quickly, quite a bit of math here. So let's do that one and then we'll do that last ACS to finish up. All right, so we have this reaction here. We've got Pb, CO3, solid, going to lead oxide, solid, plus CO2 gas. All right, and they want to know the equilibrium pressure. All right, so I'm going to leave a whole lot of room here and write down here at the bottom that K for this reaction is just going to be CO2. And if I calculate a K, and if it's gas, Kp would be equal to the pressure of CO2. So that's essentially what we're after. And we are going to use the equation. Ultimately, we are going to calculate delta G, and then we are going to use the delta G equals minus RT ln of K to get this, which is what they want. And we have two different temperatures. But before we can use this equation down here, I have to calculate delta G at both 400 degrees Celsius and 180, which means I need a delta H and a delta S, which is the approach I used once again, rather than using the heats of the delta G's of formation. So anyway, that's what I've already done, and I'm not going to go back. So, okay, so delta H, we just did one in the problem before last. We're going to need heats of formation, so I'm going to make a little table here. Heats of formation, and do products minus reactants, and we're going to do S, products minus reactants. So I'll be looking at absolute entropies and heats of formation in order to calculate those values that I gave you in class. So, okay, so the heat of formation of this lead carbonate is negative 699.1. Looking these up in the back of the book. The absolute entropy for that substance is 131. The heat of formation for lead oxide is negative 217.3, and the heat of formation, the absolute entropy is 68.7. Carbon dioxide, negative 393.15, 0.5 rather, sorry, 0.5, and the absolute entropy, of course it's a gas, much higher than the other two. All right, so let's do delta H first. Products minus reactants, so we've got 68.7 plus, oops, wrong thing, sorry. Negative 217.3 plus a negative 393.5. All right, that's your products, minus your reactant. All right, so there we are, solving it all out. That this in parentheses part here comes out to negative 610.8 plus 699.1, and this is how I arrived at a delta H of 88.3 for this reaction. So endothermic, you're taking a solid and you're essentially decomposing it, so that makes sense. Let's extend our page. Delta S, we're going to take those entropy values, products minus reactants, so 68.7 plus the 213.6 minus the 131. So that is equal to 282.3 in the parentheses minus 131. So my delta S, is equal to 151.3. It's positive, and that makes sense. We're increasing entropy by taking a solid, breaking it down into a solid and a gas. Okay, now we're going to combine those two things at two different temperatures. Remember that your temperatures need to be in Kelvin, so I'm going to do that here. 400 plus 273 is 673, and 180 plus 273 is equal to, let's see, I've got it in my work here somewhere, 453. All right, so now we're going to use the delta G equation. We're not finished. We haven't got our delta G yet. So delta G equals delta H minus T delta S. And remember, my bad, not putting in the units here. And kilojoules for delta H. Okay, so of course we've got to change the entropy values to kilojoules. Let's send that page one more time. So let's do the first one. So let's do A. So delta G is equal to delta H, 88.3, minus 673 times our delta S, which is 151.1513. All right, so delta G for A is, got that somewhere here, is equal to negative 13.5 kilojoules. So it is spontaneous at 400 degrees Celsius. B, okay, I'm going to do the same thing. So delta G equals delta H, which is 88.3, minus 453 times 0.1513. So delta G at the lower temperature is 19.8 kilojoules. So not spontaneous at the lower temperature. So we're seeing in effect here, you are seeing an endothermic reaction, delta H is positive, with an increase in entropy. Those are in that table of positive and negative values. Those are the two, I'd call them IFEs. They are dependent on temperature. So we are seeing a reaction that at 180 degrees Celsius is not spontaneous. This one depends on temperature. As the temperature increases, that second term becomes larger, that increase in entropy. And the reason why, due to this difference in units, was one of the reasons why, and entropy is very temperature dependent, so we see that it becomes more spontaneous at a higher temperature. Okay, so back to what we were after. We are after the pressure, the equilibrium pressure at the two temperatures. So now we're going to take the delta G that we calculated in each temperature, and we're going to calculate our K. All right, so let's start with A, and that is right here underneath. I'm going to take negative 13.5 equals, well, no, sorry, let me back up. I'm going to rearrange my equation, all right? This equation right here, okay? I'm going to rearrange it so that I'm solving for K. So I'm going to say ln of K is equal to delta G, and that's a negative there, over RT. So just rearranging that equation. I divided both sides by RT by the negative RT, okay? So we're going to plug in our value, which is it's a negative 13.5, so that will become positive, and the R we're going to use, and we'll write it over here at the bottom, has to be the 8.314, and that's in joules. So I am joules per, I think it's joules per K atmosphere, and this is how we're going to end up with pressure. Anyway, so I'm going to have to change my kilojoules to joules, okay? So that number, before I, rounded it off for significant figures, was 13.525. Actually, what I'm going to do is, hold on, I'm going to erase, because I was going to do it in scientific notation, but I don't really have room to do that. So we're going to just write it as 13.525. So taking that 13.5 and multiplying times 1,000 and bringing in a couple of digits that we left off before. Okay, so delta G over 8.314 times the temperature in Kelvin. So sorry, I'm running out of room here. And that temperature in Kelvin is 673, okay, for A. We're extended the page so much, it gets narrower. So then my ln of K is equal to, in A, when I do the math for that there, I come up with 2.42. Now, those of you who are rusty at some of this math, there is a Appendix A in the back of your book, has reviews some of what we've been doing here. So in order to get K by itself, what I have to do is take the antilog of the ln. So what I'm doing is I'm saying e to the ln K equals e to the 2.42. That is the antilog for a natural log. So this becomes just K, and this, when you do it on your calculator, becomes 11.25 atmospheres. Atmospheres is in that R. Okay, that's A. We're going to do the same thing in B. We're going to take this equation here and plug our values in. So we're going to say that the ln of K for our B is equal to our delta G at that temperature, which at this temperature it's negative, and so it's positive, sorry, so it doesn't go away, the negative sign doesn't go away. So I'm going to take the 19.8 times 10 to the third, leave that one in scientific notation, joules over 8.314, and its units, times the temperature, which is 453. Solving this ratio here, I end up with ln of K is equal to negative 5.25, and then I do that E thing, okay, so that I end up with K equals E to the negative 5.25, and then K, and which is equal to the pressure of the carbon dioxide, is 5.2 times 10 to the minus 3 atmospheres, which equals the pressure of the CO2. And that is number 16 done again, which was a lot of math done at the very end of class. All right. What I want to do last is a problem from the ACS. Looked over them. They look pretty easy, I think, for the material we studied from this chapter this semester. What I want to do is go back and redo something from 131. I'm teaching 131 at Bishop, and I know that I'm going through what I'm about to show you really quickly, so I think it would be advantageous to look at it again. So ACS number 9, page 50. Asks us to calculate using the delta H for a reaction using bond energies, okay? So this is a good review as we're getting closer and closer to our final. So I'm going to write the equation. N2 gas plus 2H2 goes to N2H4. And then they give you a table of bond energies, and I will put those right here. We've got nitrogen-nitrogen bond, and it's 159. And then I've got the nitrogen double bond energy of 201. And then I've got the triple bond with 941. Also, I have hydrogen-hydrogen bond energy, and it is 436. And hydrogen-nitrogen is 389. So what I think I'm going to do is give you an extra credit question on your quiz from this material based on one of these questions. There are several of these bond energy questions on that same page. So those of you who are watching the video, you get the heads up, and there'll be an extra credit question. All right, so to calculate delta H's for bond energies, it's a little different from what you do doing the whole products minus reactants thing. This is the way I teach it. You can memorize an equation, or you can realize that all of the energies on the reactant side are for bonds being broken. Okay? And if you're breaking a bond, it is going to be positive. The bonds being formed on the product side, energy is released. That's why the bonds form. And it's negative. So what you do is you add up all of the bond energies that are being broken, give that total a positive sign, add up the bonds being formed, give that a negative, and then add them together, and you have your delta H. So it's different from products and reactants. Now, the thing about this that is a good review is you've really got to think about what the nitrogen molecule, you've got to think about the Lewis dot structures in order to get this question right. The nitrogen molecule is a triply bonded molecule. Of course, and coefficients do matter. I've got two HH bonds. A hydrogen molecule looks like this. The hydrazine molecule has no double bond in it. And I can see where students would get this wrong, thinking that there was a double bond here when there's not, and we'll go why there isn't. If I add up the valence electrons here, it's 5 and 5 for the nitrogen, plus 4 for these hydrogens, each having 1. That is 14 electrons. Okay? 2, 4, 6, 8, 10, 12, 14. Let me get rid of that little negative looking thing there. 14 electrons. So this is a good Lewis dot structure. Let's do it with a double bond and show you why it's not doubly bonded. And therefore, you will not be using that nitrogen double bond energy. Okay, so here, no lone pair, 2, 4, 6, 8, 10, 12. This is 12 electrons. This is not the Lewis dot structure for hydrazine. All right, these questions are really good for a review as you're heading towards having to take the exam on all of the material. So these are our bonds. We're breaking a nitrogen triple bond. That is 941. And it will be positive. I am taking 2 times the hydrogen-hydrogen bond, which is 436. All right? That is equal to, when you add those up, you get the whole total is positive 1813. All right? Over here, I am making 1 nitrogen-nitrogen bond, so that is 159. And I am making, so 1, this is nitrogen-nitrogen, and I am making 4 nitrogen-hydrogen bonds. You really have to draw the Lewis dot structures to see this. And that's 4 times 389. Okay, add those up, and you end up with negative 1715. So again, products forming, the bonds that are forming are all negative. Bonds that are breaking is positive. Now, take these two values and add them together, and you end up with 98 kilojoules, which is choice C on that page, and that's the correct answer. So again, I'm going to give you, as an extra credit on this next quiz, one of these bond energy questions from the same material. There's several here in the ACS on this type of calculation. That concludes our wrap up for chapter 19. I think in terms of the 3 chapters that came before it and the one we're in now, that this is probably one of the easier chapters. And much of what you have to do in order to do well on this part of the ACS is go back and review your 131 stuff.